torch?
No, I used to sell a torch for camp, and that was it.
Okay.
I was,
I know it's still like a couple weeks out, but if you're available the night of the 15th, it's over at Mays South Elementary. It's kind of, it'll be the same gig as we did over at Mays Elementary. So from my perspective, I thoroughly enjoyed watching all of you do that. So if you're available, something to think about. Okay, so let's talk about the lab. So here's the big picture. So the first thing you did is you figured out the order of magnitude by changing the concentrations. So you did that, and hopefully you figured out that it was dependent upon two things: the concentration of the acetone and the concentration of the hydronium ions. Now, in this situation, the rate law works well. Here's the downfall of the integrated rate law, where it's like natural log or 1 over. That only works if you have one reactant, okay? So it's a one-trick pony. It's a good trick, but it's just a one-trick pony. So when you have a situation like this where it's dependent upon two of them, you really can't use the integrated rate law, so you're left with the rate law. And how you did this, you varied the concentrations and you isolated them and you figured out the order of the magnitude, and that's cool as well. So then you figured that out, and then you, from there, you chose a value of K, which you figured out. You chose a certain concentration of acetone, a certain concentration of hydronium, and then from there you predicted the rate. And you said, hey, this is what the rate should be. Then you said, well, the rate, based upon what we can measure, is the change in concentration of the iodine over time. Now, here's kind of the dichotomy of this, is that we chose iodine as the concentration that we can measure, but the iodine isn't part of the rate law. So what that means is that it's zero order with respect to iodine. So that's kind of the cool part about this. The iodine has to be there, and that's a common misconception. Don't think, oh, if it's zero order, we don't have to have it in the reaction. Oh, no, no. Oh, no, 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 no. Okay? No. I say again, no. The iodine has to be there. It's just not going to impact the rate of the reaction. Okay? So there's a couple of things that are wonky about this reaction. It's cool. So the two wonky things is that we're going to measure the rate based upon iodine, but it's zero order with respect to iodine. And the other thing that's wonky is that the rate is dependent upon the concentration of the hydronium ions, but the hydronium ions overall are a product in the overall reaction and not a reactant, okay? But that's what leads us to, hey, there has to be some weird things going on behind the curtain to explain why the reaction is dependent upon hydroniums, even though it doesn't show up as a reactant. Okay, so that tells us that this is not an elementary step reaction because the hydroniums show up as a product, but the reaction is dependent upon it. Okay, so typically your reaction or rate is only dependent upon the reactants. So then once you figured that out, then we said, okay, well, let's get an idea of activation energy. So this is what we're going to talk about today. So this is a nice segue into today's topic. So a lot of times when we deal with chemistry, what we'll do is we'll talk about a function of energy versus the progress of the reaction. Okay? So all the chemicals start with a certain amount of energy. They're moving, okay? It might not feel hot, they're at room temperature, but they have a certain amount of energy, okay? So to get the reaction started, you have to give it a boost. Now, in this situation, the boost isn't anything traumatic, okay? The boost is literally, hey, we just mix it together. Sometimes you have to ignite it, sometimes you have to smash things together. Sometimes, like if your car engine, you need a spark from the spark plug to ignite the gasoline and oxygen mixture, okay? So in this situation, the activation energy isn't much because literally all you have to do is just mix it together. But that doesn't mean that there isn't like a threshold of energy that has to be made. So that activation energy, if you think about it in terms of like a roller coaster, is how high the roller coaster gets lifted before you start the reaction, okay? So to calculate that, what we're going to do is that we're going to run this reaction at different temperatures. And then we're going to take the natural log of K, and then Bethany, then we're going to take 1 over temperature in Kelvin. Okay? The advantage of the Kelvin scale is 2 things. Number one, it's never 0 because that's absolute 0. The other thing is that because of that, you never have to graph negative numbers. So this is why if scientists, especially chemists, got to vote, and we don't let them, thank God, but if we did, then they would say, oh, we're going to punt Fahrenheit, we're going to punt Celsius, and we're only going to work in Kelvin, because then we don't have to deal with these annoying negative numbers, okay? Fahrenheit's the worst, because, you know, you get really cold, and, you know, in Celsius, and you get negative numbers, 0 is freezing, anyway. So, but they don't get to vote. So hopefully what your graph looks like is that you have a nice, and I've looked at some of your data, some of your graphs, and they're pretty linear, okay? It's nice, okay? Got pretty good data. So here's what I want to see. Listen to me, listen to me, listen to me. When I look at this graph, I want to see a line of best fit drawn with a what, Cooper?
A ruler.
A ruler, thank you very much, okay? Then I want to see which points you picked on the line, okay? Not your data points. You have to pick points that are on the line of best fit. That's the point of drawing the line of best fit. So you're going to come in here and you go, okay, hey, here are these numbers, okay? Because everybody's data is different. Like one group had an exceptionally long reaction time, okay? Some have very short reaction times. So I don't have an answer key in terms of, oh, this should be the scale of the graph. This should be the exact values for the temperature, okay? You all had different numbers. The only thing I can evaluate you on, and this is the purpose of any lab, is the work. Do you show me what you did? So I want to see that, and then I want to find, at some point, I want to see the calculation of the slope of change in y over change in x. This graph obviously does not go through 0, 0 for any number of reasons. So that's what you've got. Okay. Then you're going to go, oh, the slope, and this is this Arrhenius equation, which we'll talk about the broader equation today, comes from the idea that the slope equals negative E sub A over R, okay? So at this point, you have found the slope of the line. Now, here's the wonky part about this, and this doesn't happen very often. The temperature is in Kelvin, and you're graphing 1 over temperature in Kelvin. Natural log has no units, so when you find the slope of the line, the slope actually has units of Kelvin, okay? But that isn't the temperature. Even though it has Kelvin most of the time, when you look at a graph, like let's say, for example, the slope in the physics is say meters per second, you do a position time graph, and the slope is meters per second, you go, oh, that's velocity, okay? Or the slope is force per unit of time, whatever that is, that's what the meaning is. This is a very rare instance where the slope is in Kelvin, but it's not Kelvin, in the sense that it's not a measure of the temperature, because the temperature is changing, but the slope is constant. But the units work out. So to get your activation energy, hopefully your slope has a negative value to it, okay, because it's a downward slope. Chuck, were you the one that was struggling with the negative slope yesterday? Okay, you got it figured out though? Okay. So you're going to have some negative slope multiplied by the ideal gas law, 8.314 joules per mole Kelvin, okay? And you're going to see more and more and more that you really have to pay attention to the units in this chapter, okay? Because kilojoules is completely different from joules, and liter atmospheres, which is another version of the gas law constant, is completely different from joules. You have to pay attention to the units. So here's where the magic happens. The slope is in Kelvin. You multiply joules per mole Kelvin. The Kelvins cancel out. You're left with joules per mole. Voila, there's your activation energy. Now, off the data that I had when I did the lab, I got an activation energy of something times 10 to the 5th. Okay? Joules per mole. But keep in mind, say, that's a really big number. Well, you're also dealing with an entire mole of this stuff. Okay? This isn't like, oh, per like 5 milliliters. This is like per mole. So that's why that's okay that that's a big number. On number 9, on those questions on the back, make sure that you have both answers of the acetone and the water. Make sure that your 2 answers on number 9 add up to 500 milliliters, because that's what you want to mix up, okay? So just make sure you got that little check. And that's actually, I had to mix up 4 molar. That was the actual calculation that I did. Now let's talk about number 10. So on number 10, here's what I'm saying on this question. I said, okay, if, and this is a huge if the reaction was just solely first order with respect to iodine, okay? This is what I'm saying. If it was only dependent upon the concentration of, the acetone, and I've given you the value of the K, you want to calculate the half-life. In seconds, it's a really big number, like something times 10 to the 4th seconds. If you change that into hours, it's like about 5 hours, okay? So this is where an idea, a mathematical model, doesn't fit the reality of the lab. So now, mind you, this is just the half-life, okay? Half-life. So you think you guys were bad running that thing for like 23 minutes, okay? Imagine that the half-life of this thing is like 5 hours. So we would start this reaction, say at noon, okay? By about 5 o'clock, only half of it would have reacted, okay? And then by 10 o'clock, another half would have reacted. And then by about 3 o'clock in the morning, another half would have reacted. So this reaction would have taken forever to actually see a noticeable change where that thing is going to get to 0. So if you, and here's the whole point, if you look at the reaction between acetone and iodine, and you get that single displacement reaction. So it's 0, here was my thought process. So you figured out it was 0 order with respect to iodine. So then, well, everything's in a 1-to-1 ratio, well maybe it's a first order reaction with respect to acetone. Cool, that seems reasonable. We know it's not iodine, maybe it's first order with respect to acetone. And then you go, okay, well let's play the what if game. If that was the case, and the K value is 3.6 times 10 to the negative 5th, okay, which is probably about where your K values are, then the point being is that if that was the actual mechanism, the half-life, okay, is going to be about 5 hours. So the whole point of this question is going, that sounds good, but it doesn't match the reality of what we saw in the lab. Because the reaction, instead of taking like 3 days to do the lab, it might take us a week. We're going to start this thing, we'll go back in and check on it on a couple of days. Okay? All right? Okay. Got it? Any questions? Kevin?
Okay, so the H plus is a catalyst, right?
No.
Okay, it's not.
No.
Okay, so then how does it work with the products like on question 4?
Okay, so here's in the overall reaction, okay? The hydronium ions are a product, okay? So as the reaction proceeds, the concentration of your hydronium ions actually increases. But what that means is that that's the overall reaction, but there's a mechanism where the hydronium ions are actually produced, but then they get consumed later on, but not at the same rate. So the slow step is the production of the hydronium ions, and that's why it's rate dependent upon the hydronium ions.
Okay, so by putting it in a acidic solution, we sped up the reaction a little bit? Because it didn't have to produce and then use, it could just use some from the solution?
Yeah, but, yeah, so basically, yeah, we're juicing it with the hydronium ions.
Okay.
Because what the bigger picture of what's gonna happen with that is that we want the iodine to be the limiting reactant.
Okay.
So we want that to run out first, because that's what we can observe. We don't want the hydronium ions to be the limiting reactant, because we can't tell when that runs out. Okay, does that make sense?
Yeah.
Okay. All right, we're good? Any questions? Going once, going twice, so make sure you have units on everything, make sure you have shown your work, please. Kevin, stop you on the camera for a second.